Singaporean schools. One is Pathlight School, and that is in Singapore, and the other one is Anglo-Singapore International School, and that's in Thailand. We have 3 campuses, 2 in Bangkok and 1 in Nakhon Ratchasima or Korat. Right now, I am in the Bangkok campus. I'm actually in a greenhouse. Can you believe that this is a classroom? You are right. We have a classroom that is in a greenhouse. And we thought it is nice for us to present this morning's lecture from an unusual venue. This evening, I'll be flying out of Bangkok to go back home. So maybe you're a little bit surprised that I'm actually speaking to you from Thailand. Prior to doing this job, I was with National Institute of Education in Singapore, Nanyang Technological University. I was there for 10 years, and I left about 12 years ago to come back to school and try to help teachers teach whatever they teach, not just mathematics, it's overall the curriculum, how to make teachers teach what they teach in a way that can inspire students to become better learners. This morning, I'm talking to you about mathematics education, and we are focusing on mathematical processes that also overlap with our daily life and how teachers can apply this in the classroom. To me, the topic selected by PSU is a very interesting one. I will start by giving us a little bit of an overview about mathematical processes, how it is defined in different literature. Just a short one. And then we will do examples, basically to try to understand how students can make use of their everyday thinking, things that happen in their daily lives to engage with mathematical processes, and how teachers in a classroom can capitalize, can take advantage of that. Now, this is not really a lecture. If I were to do a lecture, it will be a video. The reason why we are now all together, synchronously, meaning at the same time, we are in the same virtual space, is because we want to interact with each other. So please, whenever you have an idea, whenever you have a question, please put it in the chat. And for those of you joining us on Facebook Live, you can put your comments and questions. Also, and our 2 MCs, our 2 masters of ceremonies will pick some of the questions, will pick some of the comments and ask it. So remember to ask questions, remember to share ideas, and then based on what you share, I can continue to give you further examples and further answers about the topic of mathematical processes. I think we will go on for the first half, and then we'll take a short break, and afterwards we continue to the second session. Towards the end, we have a little bit of a question and answer segment, but please, you don't have to wait until then. Please ask the question throughout the session so that I can use the content of my presentation to answer your question directly. Please, you can use any language. You can use English, ภาษาไทยก็ได้ And for those of you who want to share by speaking, you can also indicate that, and the organizers will maybe unmute you so that you can also speak, share your idea or ask your question. And you can ask it in Thai or English, it's fine. the masters of ceremony will help me with the translation. All right, let's begin the first segment, which is for me to share with you mathematical processes, how different curriculum, different countries define what it is. I do not need to tell you the one in the Thai curriculum because that one you are very familiar with. In the case of the Singapore curriculum, processes, mathematical processes, is one of the 5 components in the curriculum framework. This curriculum framework, we often call it the Pentagon framework because it's a pentagon, was introduced quite a long time ago. It was introduced the year I became a teacher, and that was a long time ago, 32 years ago, or maybe more, 33 years ago. So more than 3 decades ago, more than 30 years ago, when I just became a teacher, this curriculum framework was introduced to the Singapore school system. We are still using it today. We have undergone quite a few revisions in the national curriculum, but the framework did not change. The framework has been constant. The Singapore mathematics curriculum framework focuses on mathematical problem solving, and that is not unusual. I think every single country's national curriculum will definitely say mathematical problem solving is important. This idea started quite long ago. For example, in the United States, in America, in 1980, they have a document called Agenda for Action by NCTM that say that problem solving must be the focus. In United Kingdom, in England, there is a Cockcroft report, and the Cockcroft report say that problem solving must be at the heart of doing mathematics. So this is the curriculum framework for Singapore. Not a new one, has been around for a long time, and one of the is mathematical processes, and it includes things like ability or competency in abstracting or abstract reasoning, in abstracting and in reasoning. So they are able to abstract. They are able to look at many specific examples and go away with a rule, a principle. So they have that ability. They also have ability to reason, to give reasons. Processes is also defined as representing idea. Maybe using symbols, maybe using diagrams, maybe using language. In Singapore, it's English language. In Thailand, usually is Thai language. Communicating and representing. Also include applying and modeling. Apply whatever they learn to problem situation, and also using mathematics to model the real world. So this is how Singapore curriculum framework explain what mathematical processes are. There are other things, for example, skills. Skills include many things. The obvious one will be doing calculation or manipulating algebraic expressions. But skills also include visualizing. Skills also include using tools. Example, using technology. So in the Singapore curriculum framework, those are explained as skills. And then there is the metacognition, being able to monitor one's thinking, being able to regulate one's thinking. So these are some aspects of Singapore mathematics curriculum framework. Mathematical processes is explained quite differently in different countries. So I just want to say that there is no one precise, concise definition of what mathematical processes are. I have shared with you the one in Singapore's curriculum framework. The one I'm showing you now is the curriculum framework for the province of Alberta in Canada. So you will notice some similarities. Example, communication. It was also part of the Singapore's definition, and it is also part of Alberta's definition. Making connections, doing mental mathematics and estimation. In the Singapore curriculum, it is under skills. But in the Canadian, or at least Alberta's curriculum, it is put under processes. All I want to say is, there is no one concise definition of what mathematical processes is. It seems like in different countries' curriculum framework, they sometimes classify certain things as a process, and yet in another curriculum, they put it as a skill. But it doesn't matter. For those of you doing research, all you need to be mindful of is to make your definition clear in your study. In the literature, as you can see, different people might include slightly different things in the basket of mathematical processes. And likewise, you have in the Thai curriculum your own items listed under mathematical processes. In the Alberta's curriculum, they have 7 processes, including problem solving, reasoning. So you notice there are some commonalities. Reasoning was in a Singapore's curriculum, is also in Alberta's. In Alberta's curriculum, technology is put under process. In a Singapore's curriculum, it was under skills. Likewise with visualization. So again, all I want to say is, there is no fixed definition what a mathematical processes are. This one is from United States of America, and in the Common Core State Standards, that's their standards, that's their curriculum. In the Common Core State Standards, they have this thing called the content standards. Content standards will tell the teachers what students need to learn, and then there is the process standards, which tell teachers what processes students need to have. And there are 5 process standards in Common Core, including problem solving, including communication, making connections, reasoning and proof, and also representation. So I think you can see it quite clearly. There is some overlap among the different curriculum framework, but it's not identical. The list given in Singapore, the list given in Canada, the list we have in America, they are not exactly 100% the same. Alright? And that's because mathematical processes is a rather broad range of abilities. As long as you define it clearly in your own research, for those of you doing research, that will be good enough. But for the rest of us who are teaching, it's really not so important where we classify, for example, visualization. Whether you say visualization is a skill, is a process, it doesn't matter as long as we make sure our students become good at it. So I think to summarize, these are some things that are quite important. This morning, today, I would like to highlight some of the more important mathematical processes that students use to learn mathematics, to do mathematics, but also they use them in their daily lives. I think this is one common issue that mathematics educators often talk about, that our students do not use what they know from daily life to do mathematics. They think that mathematics is so different from their daily life that they do not use what they can already do to learn mathematics. And because of that, learning mathematics becomes quite difficult. Only if they believe that doing mathematics is using what they can do in their daily life, they have a higher chance to do better in mathematics. And that is our topic of discussion today. The connection between daily life and mathematical processes. How we as teachers can make students believe that they are related. What you know in daily life, you can use to learn mathematics. Alright? I invite you to put comments. I invite you to ask questions, whether on Facebook Live or on Zoom right now. And the Masters of Ceremony, if you see something that you think quite interesting to share with the group, please bring them up. And then I will answer or respond to the comment or question. And if we do that a lot, I believe I will have a chance to share more things than if I were just to give you a lecture. Is there anything that you would like to bring up as a question? If you have any questions, ฉายแชทได้ or you can just tell us. Yeah, you are welcome to use Thai language or English นะใช้ภาษาอะไรก็ได้นะครับ MCs, anything in the chat that you would like to bring up? Anything from Facebook Live that you would like to share at this point?
Dr. Yeap Ban Har?
Yes, please.
Excuse me. May I ask you a question?
Yes.
I am a mathematics teacher in the secondary school, and in Thai curriculum or Thai textbook, the problem solving, it's in the last chapter of the book. It's like students have to learn like basic knowledge or basic concept before they apply the concept to solve the problem. I think, in my opinion, is it right that we should like embed problem solving in every step of the sub concept?
Thank you for that important question.
Yeah, but the question is, most of Thai teacher, they think that the student don't have enough knowledge or skills or competency to solve the problem because they thought that problem is quite hard for them. So how to change this belief of the teacher and how to encourage the student to solve the problem and let them like feel like they confident they have like the confidence to solve the problem even though they don't have like they don't teach them at the end of the lesson. This is the question. And another question is, I think apart from problem solving, I think problem posting is important as well, but it's not quite famous in Thailand. Do you have any section to share about this topic?
Thank you for that question. A very good question to begin this morning's discussion on the topic. Problem solving. Problem solving is an example of a mathematical process. Some people even say that mathematics is problem solving. So in a Singapore curriculum, we did not say problem solving is a process. We say problem solving is the main thing. That is why it is in the middle of the framework. It is the thing. If we don't do problem solving, then we are not doing mathematics. And we use mathematical processes to do problem solving. In the case of Canada, problem solving is considered a process. Also, in America, problem solving is considered a process. It doesn't matter. But we all know that problem solving is an important part of mathematics and definitely is considered to be a mathematical process, or at least require mathematical processes. Everyday life. It's quite easy to understand that we do problem solving in our everyday life. I don't think that needs much explanation. Every single day, we faces all kinds of problems. From being late because stuck in the Bangkok traffic jam. That is a problem. And we need to solve that problem, especially if we are running late. Or sometimes for those of us who drive, the car decides not to cooperate and not wanting to start in the morning. We face all kinds of problems in our everyday life. So it is quite easy to see that something we do in our everyday life, solve problems, is also what we do in mathematics. I will now answer the question. The first part, as our friend mentioned, some teachers teach problem solving at the end of the chapter or the topic. That model is called teaching for problem solving. That means we teach them algebra. Why? So that they can solve a problem. So we always teach them something. And how we teach? Maybe we give a lecture. Maybe we explain to them. But we teach them the content. Usually using the traditional method. Lecture or explain. And then later, we give them some problem to apply. So that model is called teaching for problem solving. There is another model that you do problem solving every day. It is called teaching through problem solving. I will now do an example, and later we will address the other two parts of the question, the belief system. The belief system of teachers. that some students are not good in mathematics and also problem posing. But let us first talk about the first mathematical process, problem solving. Secondary school example. But maybe I start with a related primary school example. So I may be a grade 4 teacher, ประถม4. So maybe I'm teaching a grade 4 class, and I will say, boys and girls, today we are going to solve a problem. The problem is I have some square tiles. You can see how many square tiles I am giving you. I am giving you some square tiles. I'm giving you 12 square tiles. Our problem today is, can we rearrange the square tiles to make a rectangle? That's our problem for today. Try to make a rectangle using 12 square tiles. And once I tell students the problem, they have the square tiles. I mean, they can just make from paper, just cut out from paper, or just use the memo paper, anything. Or maybe your school have the plastic ones, or maybe some of you use virtual manipulative, like what I am using here. It doesn't matter, but students must have some concrete materials, and I ask them to work with their friend. Maybe 2 of them work together, maybe 3 of them work together, sometimes 4 of them work together. And I leave them alone for 10 minutes. So my students will know the first 10 minutes of the lesson, I am not going to help them, because I will help them later. So it's a routine. Every day, we start with a problem. Problem today is make rectangle using 12 square tiles. And I leave them alone. 10 minutes. They talk, they try. Some of them record somewhere. In Singapore, we call it the math journal, the mathematics journal, just a notebook. Some of them record using symbols. Some of them record using words. But whatever the case is, I leave them alone for 10 minutes. And after 10 minutes, I gather them in front of the class. In Singapore school, we have some space in front of the class. And this is where the teacher gather the kids. So we are close together and we can talk. They can talk. When they are close together, they talk, their friends can hear them. When they are all seated far away from each other, you know, children's voice sometimes not as clear as ours. So when they are far away, they cannot hear what their friends are saying. But when they sit near to each other, the teacher will say, okay, you please share what you did with your friend. And the boy may say, we make the rectangle like that. And the teacher say, what do you mean by like that? And maybe the student show. Oh, you mean you make 2 rows of 6. So they make 2 rows of 6. I can also write it like that. 2 rows of 6. Oh, thank you. So that is one idea. I'm not sure whether you agree with our friends, but you can check whether 2 rows of 6 is 12. Whether 12 is 2 rows of 6. I wonder if there's another way to solve the problem. the teacher might ask. Because in our class, we have a routine. The routine is always solve a problem in more than one way. So we got one way already, and that's very good. And some students may say, or the teacher may say, oh, this group, tell us what you did. And they say, we did the same. But we also do more rows. We also do 4 rows of 3. Oh, the teacher said, do you mean something like that? You make 4 rows? 4 rows of 3? So are you saying that 12 can also be arranged as 4 rows of 3? And some students said, but teacher, we make 3 rows of 4. Is it counted to be the same or not? And the teacher may say, class, what do you think? Some friends say they make 3 rows of 4. Would you consider that to be the same or different? It doesn't matter to me. Some of you may say, I think it's different because 4 rows of 3 look like that and 3 rows of 4 look like this. And we think it's not the same. And that's okay. In our class, we can agree to listen, but we don't have to agree. We agree to listen, but we don't have to agree. So some of you say, we think it's different. But some of you say, we think it's the same. Because you can rotate one, and it will look like the other. But I leave it to you, okay? To decide whether you want to think 3 rows of 4 and 4 rows of 3 to be the same or not. Colleagues, I am demonstrating how a teacher teach a new topic. The topic is factoring, finding factors in Prathom. And this is the first lesson. And the teacher did not explain to the student. The teacher did not do the traditional lecture. Instead, the teacher gave them a problem. Colleagues, do you see what I mean by teaching through problem solving? We use a problem for students to learn something. So this is different from the model that our friend was talking about, that in many Thai textbooks, the problems are at the end. Here, the problem is in the beginning. In the first lesson to learn finding factors, or factoring, or factorization of whole numbers in Prathom, the teacher used a problem. And in secondary school, the teacher can do the same lesson, but for algebra, for algebraic expression. The teacher may say, well, today we have an expression square of x, which means this is x and that is x, isn't it? That's how the square has an area of square of x. So we have square of x. We also have rectangles like this. And rectangle like this one is the same length, so it must be x. And if the area is x, that means this must be 1. So in this rectangle, this is x, and that has a side of 1. In our problem today, we have a square of x, but we also have 5x, 5 of x. And we have some ones. The question I have for us is this. The problem I have for us is this. How many ones can we add to this? How many ones can we add to this? So that we can rearrange it to make a rectangle. Remember, more than one answer. How many ones can I add to this? How many ones can I add to a square of x, this one, and 5x? Can I add 3 ones? And then I can rearrange to make a rectangle. Can I add 4 ones? Can I add 5 ones? Can I add 6 ones? Can I add 7 ones? See how many you can find. The problem is, how many ones can I add to a square of x and 5x? So to a square of x and 5x, how many ones can I add to it? And then again, I let the students use the concrete material. You can use the virtual one, like what I'm doing now. You can just give them the plastic ones, if your school have them. Or you can just make using cardboard or paper. Just cut out. When I first started teaching, we don't have resources like algebra tiles, you know, the one you buy. So we just make them. We just draw and we cut out. And we use them. Huh? So the students will go and work with their friends. 10 minutes in secondary 2, usually in Mathayom Song, in grade 8. It's the first time they learn about finding factors for algebraic expression, including the one for quadratic. So later, they meet me and their friends in front. I always like to have the first part, they are in their table, in groups, or in pair, and the second 10 minutes, they come to the front. I like my students to move. Every 10 minutes, they move. Because when they sit down for too long, they lose their attention. Also, when they are in the same spot, sometimes they don't know what they are doing. But my students know, when they are seated there in their table, the expectation is they work independently. I don't help. So they make use of the physical space to remind them what they are supposed to do, the expectation. And when they meet in front, they know I am helping them. They know they're supposed to listen to their friends. They know they're supposed to be sharing ideas. So second 10 minutes, they come to the front and I say, group 4, what's your idea? And group 4 say, actually we didn't add any. Our answer is 0. Oh, class, is it possible to arrange this to make a rectangle? And everyone agrees. Yeah, it's easy. You just put them together. See, it's a rectangle already. And the teacher say, oh, how interesting. Your rectangle has an area of this. That's the area of the rectangle. And do you know another way to tell people the area of a rectangle? And they all say, yeah, the length times the width, the product of the sides. Oh, do we know how long this side is? And they say, yeah, we know. That's x. And how about the other side? Do we know how long this is? And they say, yeah, this is x. And then this one is 1, 2, 3, 4, 5. So we have 5 more than x. Oh, so are you saying that we can also say the area is also the product of the two sides? Or some of you prefer to write it the other way? Oh, that's good. Thank you very much. So that is method 1. Method 1, we don't have to add any constant. Square of x and 5x is already good enough. And we are able to see that the two sides to the rectangle is as given. How about group 6? I may ask the student, do you have a different answer? And they say, yeah, we added some. We added a few ones. We added 6 ones. Another group may say, class, do you think when you add 6 to square of x and 5x, so if you already have this and you add 6, is it possible to rearrange that? Is it possible to rearrange all that into a rectangle? I'm not sure, but that's what your friends say. We can try. Do you think it's possible to put 6 ones into the empty space so that we can make a rectangle? Can you imagine whether it's possible or not possible? And I let the students think a little while, and afterwards they will continue and they will say that, well, that rectangle, the area, can also be written as the product of this side and the other side. So they will see, oh, okay, I could get it as x plus 3 for one side and x plus 2 for the other side. And if you are not sure, they can try and see that, well, that is true. The first example I use in today's lecture is on a major mathematical process called problem solving. And I was using that example to illustrate what we mean by teaching through problem solving. So in that case, we are getting students to learn something through problem solving. The question asked earlier was, the traditional Thai textbook focuses on teaching 4 problem solving. We teach first using lecture, using explaining, and then they try to solve the problem. The one I demonstrated using the lesson on factoring from Prathom, make rectangle for 12, also for Mathayom, factoring, quadratic expression using algebra tiles. Those are examples of teaching through problem solving. I imagine teaching through problem solving have some advantages. The obvious one is the students do problem solving more. Every day they are doing problem solving. To learn something new, they do problem solving. At the end of the chapter, they also do problem solving. In the traditional approach, teaching 4 problem solving, first part, no problem solving. Only have problem solving at the end. So students who learn mathematics through problem solving have more practice in problem solving. And if they are better in problem solving, we can understand why. They have more chance. They have more opportunities. They have more time to do problem solving. Yeah? Also, quite important is about the belief system. Many teachers think that some students cannot do mathematics. Actually, they can. What they cannot do is they cannot understand the teacher's explanation. Is not because they are not good in mathematics. They cannot understand the teacher's explanation for many reasons. Maybe the student's language not very good yet. And the teacher used language to explain. Maybe the teacher's ability to explain is not very good. Whatever the reason is. It is not because the student is not good in mathematics, but it is because the student cannot understand the teacher's explanation. But why must the teacher use explanation? The teacher can do so many other things. The teacher can give students concrete materials. The teachers can use visuals. The teacher can use conversation. The teacher can do so many things. Why don't the teacher listen to Brunner? Because Brunner will say, use concrete material, use diagrams, don't use explanation, student can understand. Why the teacher don't listen to Vygotsky? Because Vygotsky say, when students talk with each other, they can learn mathematics. Why the teacher instead tell the students, keep quiet, don't talk, listen to me. There is no learning theory who say, listen to me. There is not a single learning theory in mathematics education that say, students keep quiet, listen to the teacher. Don't have. If the teacher used that method to teach, students keep quiet, don't talk, listen to teacher. The teacher is not using pedagogy. I am not sure where that comes from, but no learning theory allow us to tell students, keep quiet, don't talk, listen to me. Giving explanation is not backed by any basic learning theory. There are at least 3 learning theories that if a teacher uses, we can almost guarantee all students can learn. So I'm answering the question about belief system. Our topic today is mathematical processes and how to help students relate everyday life with mathematical processes. What happens in everyday life? We have conversation, we talk. Everyday life is about talking. And we learn things because we got a chance to talk with other people. That is Vygotsky's theory. It's everyday life, it's also learning mathematics. What is everyday life? We like to touch things. We like to hold things. We are physical. Think about everyday life. Can you learn to be good in basketball by just watching people explain to you what basketball is? No, you have to play basketball. Can you learn to become better in cooking by listening to someone tell you how to cook? No, you have to cook. Then you become better. In our everyday life, we become better because we do. But how come in mathematics, we tell students, listen to me. I explain to you. Why is it so strange that in mathematics, we do something that we don't do anywhere else in our daily life? Where in our daily life, we listen to someone and then we become good at it. We become good in basketball because we play basketball. We become good in cooking because we cook. And we become good in mathematics because we do mathematics. We do mathematics by using our hands. We do mathematics by drawing. And we do mathematics by using symbols. We do mathematics using all the three forms of expression. Not just symbols, also language. Not just symbols, but also visuals. Not just symbols, but also concrete materials. Thirdly, there is Dean's. Dean's theory tells us students learn because they explore. So you notice the two examples I gave you? I gave you something and I say, okay, go and talk to your friends. Go and explore how many ones you can add to make a rectangle. And they found out I can add nothing, 0. I can also add 6. And those are at least 2 cases where they can make a rectangle. Or the students who are younger, I give them 12. And I say, go, explore. And because they explore, they found, maybe I can make 2 rows of 6. I can make 6 rows of 2. I can make 3 rows of 4. 4 rows of 3. I can make 1 row of 12. Or 12 rows of 1. Exploring. Something quite important about teachers' belief. Why do teachers believe that students learn through explanation? Where do they get that from? Did they not learn about Brunner? Because Brunner didn't say students learn from explaining. Sorry, students don't learn from explanation. Students learn from concrete materials. Students learn from visuals. Students learn from having conversation. That's Vygotsky's answer. And students learn from a chance to do exploration. So learning theories tell us many things. I will stop here for you to say something. MCs, do we have anything from the chat that you would like to share with us? Or any of the participants would like to share some thoughts or even some question? Anyone? MCs, anything you would like to add at this point? Anything in the chat room? If there's something in the chat room, the MC, please share them with me.
So, Dr. Yeap Ban Har, based on my question, I would like to summarize or recap what I get from your explanation, from your answer. Could you please allow me? Because
yes,
I would like to make sure that I understand what you are sharing. Yes. So it means that
can you do it in Thai language, please?
ได้ครับก็คือเหมือนกับว่าผมถามไปว่าโดยปกติแล้วเนี่ยในสไตล์การสอนของไทยนะครับเรามักจะสอนการแก้ปัญหาเนี่ยในส่วนท้ายของคอนเซปต์นั้นๆหรือว่าบทเรียนนั้นๆทีนี้ท่านก็บอกว่าการสอนเนี่ยเราสามารถถ้าการสอนแบบนั้นเนี่ยมันคือการสอนเพื่อแก้ปัญหาแต่ว่าจริงๆแล้วเราสามารถสอนผ่านการแก้ปัญหาได้ซึ่งสิ่งที่ผมได้จากคำอธิบายของท่านก็คือว่าหนึ่งเลยก็คือเราเนี่ยสามารถใช้ปัญหาเพื่อใช้เป็นเครื่องมือในกระบวนการเรียนการสอนได้การแก้ปัญหาไม่ใช่เพียงแค่เครื่องมือที่ใช้ในการแก้ปัญหาเท่านั้นนะครับแต่ว่าการแก้ปัญหาเนี่ยสามารถใช้เป็นเครื่องมือสำหรับการเรียนรู้ของนักเรียนได้ด้วยแต่สิ่งที่ผมเห็นก็คือว่าปัญหาที่เราใช้เนี่ยคุณครูจะต้องทำกันบ้านกับมันพอสมควรก็คือคุณครูต้องรู้ว่า ความรู้ก่อนหน้านี้ของนักเรียนคืออะไรแล้วคุณครูสามารถจะสร้างปัญหาที่สามารถเป็นเครื่องมือที่ช่วยให้นักเรียนเชื่อมโยงความรู้เดิมกับความรู้ใหม่ที่จะสร้างขึ้นในห้องเรียนนั้นๆได้อย่างไรอันนี้คือสิ่งที่ครูจะต้องไปทำกันบ้านเพิ่มนะครับอันที่สองที่ผมได้ก็คือการเปลี่ยน culture หรือว่าเปลี่ยนห้องเรียนนะครับจากการที่ท่านได้แชร์เนี่ยก็คือท่านพบว่าในห้องเรียนของท่านเนี่ยเด็กจะรู้บทบาทของครูแล้วก็บทบาทของตนเองแต่ในห้องเรียนไทยเนี่ยจริงๆแล้วเด็กก็คือเป็นผู้รับแต่เพียงอย่างเดียวโดยส่วนใหญ่นะครับอาจจะไม่ใช่ทั้งหมดคือเด็กเป็นผู้รับแล้วคุณครูเนี่ยเป็นผู้ให้ก็คือเป็นผู้ให้คำอธิบายแต่การเปลี่ยนวัฒนธรรมการเรียนรู้ในห้องเรียนของเราเนี่ยให้นักเรียนเป็นคนลงมือทำนะครับแล้วคุณครูก็เป็นผู้ที่กระตุ้นโดยใช้ปัญหาหรือใช้คำถามแล้วเรียนทำแล้วก็สร้างคอนเซ็ปต์อันนั้นเนี่ยอาจจะเป็นเรื่องที่ต้องใช้เวลานิดนึงในห้องเรียนของเรานะครับแล้วก็ท่านก็พูดถึงการเรียนคณิตศาสตร์ที่เราต้องเรียนรู้เราไม่ใช่เรียนรู้ผ่านการอธิบายของครูเนาะเด็กเนี่ยเรียนรู้ผ่านการลงมือทำนะครับผ่านการ visualization หรือว่าการเห็นภาพการนึกภาพนะครับแล้วก็ผ่านบทสนทนาหรือว่าเป็นแนวคิดของไวกอสกี้ที่เป็น social constructivist ก็คือเรียนรู้ผ่าน interaction ระหว่างกันในห้องเรียนนะครับอันนี้คือสิ่งที่ผมได้จากการอธิบายหรือการแชร์ของดร.ยับนะครับขอบคุณมากเลยนะครับ Thank you so much ดร.ยับ
Thank you for that summary. I think it's a nice summary, also alluding to the fact about the culture of the classroom. No? So we have so far talked about the process of problem solving, and you just also mentioned another important process of visualization. So visualization is another example of a mathematical process. Yeah? I will explain a bit and then I'll do one problem with you. So visualization is what the mind can see that the eyes cannot see. So visualization is what the mind can see that our eyes cannot. So our eyes cannot see it, but our mind can see it. Clearly, visualization is needed for something abstract. Because something abstract, our eyes cannot see. Because it's abstract. So to be able to understand something abstract, we must be able to visualize. Example, say in chemistry, atoms are not abstract, but they are so small. So small you cannot see using your eyes. So if I can understand about atoms and atomic structure, about the nucleus, about the protons, the neutrons, and the electrons in a different shell, if I can understand that one, it's because I can visualize. Because I cannot see an atom. The only way I can understand atom is because I can visualize. But at first I cannot visualize because I'm still young. I'm still learning. What do the teacher do? Do the teacher try to use language to try to let the students imagine how the atom look like? We don't, right? We give students model of the atom. Maybe we use ping pong ball and we show students about the nucleus and the electron. Or with technology, we can show them animation about how the atom look like. Or we can show them diagrams in a textbook. As the English saying goes, a picture paints 1,000 words. A picture paints 1,000 words. So why will the teacher try to explain what an atom is when the teacher can use diagrams or animation or even better, a model. So visualization we need in mathematics, but you also need it in chemistry or physics. There are many things in physics that don't exist because they are not matter, like electricity, like forces, like magnetic field. You cannot see it because they are not matter. So you cannot see it. You cannot see them. How to understand them? Visualization. So you need visualization in mathematics. You also need visualization in physics. Or biology. What's the best way to learn digestive system? What's the best way to learn digestive system of a frog? You catch the frog. You pin the frog down. You cut the frog up. You open the frog up. And you can see the digestive system. That's the best way to learn about digestive system of a frog. How about learning digestive system of a human? Oh, you cannot catch a human, pin him down, cut him up. That's called murder. It's illegal. You cannot do that. So how do teachers help students learn about digestive system? We usually cannot see digestive system of a human. Yeah, we can use diagrams in a textbook. We can give them animation using technology, or we can give them a model, a plastic model. Will the teacher use words to try to explain all the time? If you try to use words all the time, then the students may not understand it completely. So I am just explaining, giving you examples, how visualization, a process that we use in everyday life or we use in other subjects, also use in mathematics. Everyday life, you visualize every day. In English, we use the word imagination. Imagine. When you are doing imagination, you are visualizing. When you are trying to think, where did I put the key this morning? You are visualizing. You are trying to visualize something that happened already before. It happened already. So your eyes cannot see it. Gone already this morning. Happened already. And then you try to imagine, oh, what did I do this morning? I remember I had the key in my hands. What did I do? Oh, I walked to the kitchen. Oh, I went to brush my... Oh, what did I do this morning? So when you try to do that, which happens quite often, you are using the same part of the brain for visualization. So visualization is something we do in our everyday life. Visualization is also something they need to learn other subjects. Visualization is also needed to learn mathematics. What do the teacher do in class? Let me now demonstrate with another problem, and then we're going to take a break. Class, today I have a problem for you. The problem is about squares. The problem is about squares. I have a straight line, and the straight line is 29 centimeters. So maybe I call the straight line AB. I mean, that's one common way we name line segments. Point A, point B, So the line AB is 29 centimeters long. Nah? So that's what we know. In fact, that's all we know. And I have squares. I have squares that I draw like this. I have 3 squares. Okay? So those are 3 squares. The problem is find the perimeter. Find the perimeter of the figure. So we say the figure consists of three squares. So that's our problem for today. The figure consists of 3 squares and AB is 29 centimeter. And the problem is to find the perimeter of the figure. And I let the students go and talk for 10 minutes. What I want to now demonstrate is application in the classroom. Our topic today is mathematical process. One mathematical process is visualization. Visualization, we use it in our everyday life, as I explained to you. Visualization, we also use it in other subjects, not just mathematics. What does it mean for teachers? The teacher may present a problem like that. Do I now explain? No, I don't explain. According to learning theory, what should I do? Number 1, I should give students some time. I should give students some. That is from the theory of Piaget. Piaget talks about processing time. So I should let the students have a bit of time. But I say 10 minutes. I give them the problem. I give them time. Why do I give them time? Piaget said so. In a traditional classroom, we ignore Piaget. We don't care about Piaget. In a traditional classroom, I come to class and I say, good morning. Sawadee krap. Everyone listen to me. We will start the lesson now. There's no processing time. We expect students to be like a machine. We just turn on the button. Now we learn. Unfortunately, the human brain is not a machine with a switch like that. They need a bit of time. They need time to bring prior knowledge into the short-term memory, into the working memory. Yeah? So they need processing time. So I give them the problem, I give them some time, and I let them explore. They will try. They won't get the answer straight away, but they will try. And maybe they don't get. Then they try again. And doesn't matter. They will have a chance to just explore. And they talk. They interact. That's Vygotsky. And they have a diagram. Maybe some of them will cut the diagram out. Now they have concrete materials. It's up to them. But they are not just listening to the teacher. So after 10 minutes, I want to now emphasize visualization. So I say to the students, all right, let us now discuss. Can somebody tell us, not the answer, we don't want the answer. Can somebody tell us one useful thing? Means, please give us a hint. Give us a hint to help us who cannot solve the problem yet. Anyone would like to give us a hint? You can just unmute and tell us. Or if somebody give a hint in a Facebook Live or in a chat, the MC can tell me also. Can anyone give us a hint to help us find the perimeter? We all know what perimeter is, right? Perimeter is this one. Perimeter is all the lengths. All this, right? So that's perimeter, right? Yeah. Anyone have a hint you want to share with us? Not the answer, just a hint.
Good morning, Doctor.
Good morning.
Yeah, okay, now, I'm from Isan region, but I would like to share some hints for this problem. So that's because there are 3 squares. So square each sides are equal.
Okay, stop, please. I press a pause button for you. Oh, so one hint your friend has given you is squares equal sides. So the hint is this side, same length. I use another color. The hint is this side and that side, same length. This side and this side, same length. This side and that side, same length. Okay, so that is the first hint. Do you want to continue?
Okay, thank you for the opportunities. So for me, based on my knowledge right now, I'm going to give some like X, Y, or Z to show the length of the squares, 3 squares.
Okay, thank you. So somebody say that, well, I can let this be, let's say X or Y or Z. So X will be how long this is, Y how long that is, and Z how long that is. Okay, so that is one method. Those of you who can continue using that method, yeah, that will be helpful. So can you imagine somewhere else in this square where you can see X? So your friend say, let this side be X. Can you see more X on the diagram? Okay, anyone else who maybe did not use X and Y, but you have a different way to try to solve the problem? Thank you for that. Those 2 hints. The first hint is, remember, square, sides are equal. And then second hint is, you can let the side be X or Y or Z. Huh? Maybe one more? Someone else can just unmute yourself. ใช้ภาษาไทยก็ได้นะ You can use Thai language as well. Anyone else have a different hint? MCs, anything in the chat? Whether the Facebook Live or in Zoom? Anyone else would like to share a different hint
สวัสดีค่ะ
continue
ก็
เชิญครับ
วิธีคิดนะคะก็คือว่าเราคิดเส้นสีเขียวเป็นเส้นรอบวง1เส้น
Okay, so the hint is, oh, that green line is just one line.
ใช่ค่ะ แล้วก็ตัวที่ตรงข้ามกับเส้นสีเขียวก็มีความยาวเท่ากับเส้นสีเขียว
Oh, stop there, please. So that's a big hint. Like opposite the green line, there is also 29. Can you imagine? Can you see more 29 in the diagram? Oh, so that's a very useful hint. Go and find more 29s. So this is 29. So your friends say, look, there are more 29 in the diagram. Oh, some of you saw it already. Can you imagine which are the one I'm going to highlight to show a 29? Can you read my mind? Were you expecting me to do this? Oh, so your friend suggests that there are other 29 in the diagram. There is 129 already given, and then now we just found out another 29. Can you imagine when we try to move this one down and this one? Can you imagine it moving up? And this one, can you imagine it moving down? And it will then become something on the green line. Okay. So are you able to see how many 29s altogether that make the perimeter? I leave that to you. So those are very useful hints. Method 1, using the X and the Y and the Z, and try to find more X, more Y, more Z that make up perimeter. And the second method is imagine. There are more 29 in the diagram. Oh, I saw another 29, but that one I'm not sure. So can you check whether I'm thinking correctly? I know this and that are the same length. So I'm thinking this one. Can you now read my mind? Which are the pieces I'm going to pick to make 29? Were you expecting me to say this also? But will these two give me 29? Not yet. Yeah, I'm going to pick one more. Can you guess which one I'm going to pick? Were you guessing I might pick this one? But I'm not sure about this one. Can you check for me whether it is definitely 29 or not? And what kind of reason you can give to say it's 29 or not? Right, colleagues, I was just demonstrating application in the classroom. To summarize, we know visualization is an important mathematical process. We know that visualization happens in our daily life because we always have to imagine. Oh, imagine what happened this morning. When you try to recall what your friend told you this morning, you're imagining, you're visualizing. Whenever you try to recall something, you are visualizing. Like, oh, what was it that happened this morning? My friend said something. So visualization happens, I think, all the time in our daily life. We also saw it being used in other subjects. Finally, I demonstrate application in the classroom. What does it mean to the teacher? And I was demonstrating to you. I did not tell you what to do. I show you what a teacher might do. So you might notice some of the things I did as a teacher. If you can, please share in the chat or comment some of the things you notice I did as a teacher. So the question for you to contribute to the chat, to contribute to the comments is, what did the teacher do to make students better in visualization? All right?
แล้วในช่วงนี้นะคะก็จะเป็นช่วงหลังแล้วเดี๋ยวเราจะกลับมาพบกับวิทยากรของเราอีกครั้งหนึ่งโดยที่เราเนี่ยยังค้างคากันอยู่เลยค่ะคุณเอ็มเมื่อสักครู่นี้นะคะก็มีคนได้ให้คำใบ้ไว้นะคะสำหรับโจทย์ข้อนี้ก็คือ2คำใบ้เนาะแล้วเดี๋ยวผลเฉลยโจทย์ข้อนี้เนี่ยมันจะเป็นยังไงเดี๋ยวเราจะกลับไปฟังใช่ไหมคะคุณเอ็มใช่
ครับแล้วก็ไปฟังกับท่านดร.เยบันฮาเลยนะครับ
ค่ะขอเรียนเชิญเลยค่ะ
Welcome back to the next part of our session. So I believe there are some questions in the chat. Would you like to let us know what the questions in the chat? And those of you who want to ask more questions, you can also unmute yourself, yeah? But I think there are 2 questions you mentioned in the chat. Can someone let us know what the questions are? Who is going to be letting the group know the questions?
Dr. Yeap,
Yes, please.
I saw the question in the chat box.
Yes.
I think it's very interesting. The question is, what is the most challenging problem for mathematics teacher in Singapore in teaching online during this pandemic?
First, I must say that Singapore schools did not close for very long during the pandemic. We closed for a little while, but we did not close for very long. Okay? I will answer the question in a little while, but I just want to say that we did not have to close the school for very long. Secondly, every year, all Singapore schools will practice online learning. This has happened for many years already. So every year, even though there's no pandemic, every year we have 1 week where students don't come to school, but they have lesson online. That is because, just like everything, like fire drill, before the fire, you must practice first, isn't it? You cannot wait until the fire and then, okay, students, let's try to save ourselves. And I don't think that's a good idea, right? Same with other things. Like some countries, they have earthquake. So we have earthquake drill. Singapore, we don't have, so only fire drills. But lately, we also have drills for terrorist attack because, the world nowadays is quite complicated. So anyway, for online learning, we also have drills. That means before the pandemic, every year, 1 week, the school will close. Not close, but the students don't come to school. And they learn from home. Online learning. In Singapore, we call it home-based learning, HBL. Nah? Because we have done it for many years already, we know the problem. So in the beginning, we know the problem. The problem is students don't know what to do when they are at home. And the teacher cannot help because the teacher is not in the same room. The students were not independent. Secondly, they found that some students will switch off the camera and we don't know what they are doing. So the second thing is the teacher cannot see what the students are doing. Thirdly, the teachers do not know how to use the online tool, and we cannot make them talk. In class, very easy. Sit together, we talk. But now, how do they talk? So the teacher did not know how to use the online tools to make them have conversation. So these were the three problems that the teachers found out about online learning. Fortunately, they did not find out during the pandemic when the lesson had to go on for 6 weeks, maybe 4 weeks. They found out before. 5 years ago, 6 years ago, we've been doing this for maybe 8, 10 years already. Every year, we practice online learning. And because we practice, we found out, number one, I think in class, we guide the students too much. That is why when they are not with us, they don't know what to do. So the teachers begin to think or understand. Actually, very important to cultivate ability to be independent. Students who go through traditional classroom are less independent. Why? Because every day, all they do is listen to the teacher. The teacher tells them everything. But students who do the lesson the way I describe it to you, 10 minutes, you are on your own. I don't help you. Every day they get 10 minutes practice to be independent. And the 10 minutes all add up. And eventually, they are more independent than otherwise. One important point, classroom application. One important point about classroom application from this morning's session is make sure our routine will make students become independent. And I'm glad to hear during the break, the students talk about the open approach. I think what I'm sharing with you is like open approach. Here is a problem, the students work, and then we share. When students go through lessons like that all the time, when they are at home or wherever they are, it doesn't matter. Because every day they do the same thing. Every day, the teacher gives them a problem. It's open. And they discuss with their friends. And later, we discuss in a big group. It doesn't matter online or in class, because they do this every day. I am so happy I hear about the students talk about open approach. I hope you do this every day. I hope you don't do this only once a year or during the project. If you do this only during the project, the effect will not be seen. If you do the open approach every day, your students will become independent. This is the first problem Singapore teachers, actually teachers around the world, encounter during online learning. Students are not independent. Related to that is, students are not involved. That is why they switch off the camera. And that is because the teacher was doing a lecture, explaining. But if you ask students to do, maybe use a breakout room. Say, okay, 4 of you go to the breakout room. And they talk to their friends. Or you can use a platform where you're able to see what the students are doing. Example, those of you who use Google, you might also use Jamboard. So Jamboard is something that the students can write, and everyone can see who writes what. So you can say, okay, 4 of you, 1 of you use green, 1 of you use blue, 1 of you use red, 1 of you use black. And the teacher can just see who is writing what. Or if you use a Zoom breakout room, the teacher can visit the breakout rooms, and we can hear what the students are saying to each other. It's no different when they are in a class and the teacher walks from group to group. But with technology, it's even better. You can see everybody's work at the same time. And you have a close-up of what they write. When in class, you just look over their shoulder, sometimes not so clear. But on a technology platform, it's so clear what they are writing. So that is another problem. The teachers say that they cannot see what the students are doing. They cannot see what the students are, or cannot hear what the students are saying. But nowadays, Zoom and other platforms, they have so much improvement that those are no longer an issue. You can see, you can hear. The important thing is the teacher must realize online learning must involve the students. Example, I try to involve you today by asking you to use a chat function. But for younger children, you must involve them even more. So you cannot do lecture. You cannot do explanation. You can do explanation as a summary. You can tell the students, all right, we are finished with our discussion today. For the summary, please watch the video. So they go to watch a video for the summary. The teacher don't have to do it in a synchronous way. Right? Finally, teachers struggle because they find it very hard for the students to talk. And again, that issue is not a problem now because of the breakout rooms. So I think the problem is when the teacher try to keep the whole group together, and then the issue of different students want to talk. And, you know, sometimes they forget to switch off the mic or all the technical issues. But nowadays, with smaller group, like breakout rooms, that's no longer a problem, right? Something else?
Hello, Prof. It is a question from Facebook Live from Take a Smile. The question is, for many children who don't like math, just because they tend to think that they cannot be used in everyday life other than adding and subtracting numbers, what advice should we give to change the minds of these children?
What we can do to change the mind of children who think that mathematics cannot be used in the real world? That is because they learn mathematics as a procedure. They learn mathematics as steps. They learn mathematics as tricks. They learn mathematics as formula. When students learn mathematics like that, they will not be able to use them. Because in the real world, we don't have a formula. We don't have a procedure. We don't have tricks. We don't have steps to do things. When students learn mathematics as thinking, they know they use it every day because we think every day. Many teachers think of application of mathematics as something direct. Oh, I learn to subtract. Why? Because when I buy something for 89 baht and I pay 100 baht, I subtract. Many teachers think of using mathematics like this. How many of you actually subtract when you try to figure out the change? Most of us don't even care what the change is. You just put out your hand, the cashier give you back money. You never do subtracting when you pay the cashier, and the cashier also didn't do subtraction. The cashier key in the cash register, and the cash register will tell the cashier how much money to give you back. So it is not true that you learn subtraction so that you know how to calculate your change. Nobody do subtraction when they pay money at 7-Eleven. Nobody. I don't think many people do it. Okay, maybe some people do it. But definitely the cashier did not do it. The cashier used the register to tell how much change. And I don't know about you, I have never once done subtracting after I pay the money. I just make sure I pay enough and then I get back some money. Sometimes I look at how much I get back roughly. But I don't think I've ever done, oh, what is 100 minus 89? Oh, 100 minus 89. I put one on top of the other. Oh, 100 minus 89, I need to, I don't do all that. I don't think anyone does that. Yeah? So I think many teachers misunderstand what we mean by using mathematics in our daily life. Using mathematics in our daily life is using mathematical processes like visualizing, like problem solving, that we do in mathematics, but we also do in our daily life. What does it mean? It means when we teach a lesson, like the one we did a while ago, the teacher wants them to visualize. Why? Because visualizing is what you do in your daily life. So what does a teacher do? The teacher asks questions. Can you imagine? So the teacher is trying to train the children's mind. Many of us think of, I must make students see that they use subtracting in their everyday life. I must help students see that a geometry problem is used in everyday life. It is not like that. Helping students see that mathematics is applicable to daily life is today's topic. Letting students see that what they do, example, visualizing in class, is also what they use every day. Short answer is, if the teacher is making the students think, then those students will see that mathematics is applicable. Don't try to tell them, oh, you learn quadratic equation so that you can play basketball. Because when you throw the basketball, it's a parabola. Yeah, it's true. But nobody playing basketball is thinking about quadratic function. Nobody. Right? So many teachers misunderstood that idea. We think in a very literal way. I teach them angles in polygon. I must show them how they use that formula in their real life. It will never happen. And no wonder the students don't believe us. We must understand that using mathematics in the real world is using the same thinking process. In mathematics, I visualize. In real world, I visualize. In mathematics, I solve problems. In real world, I solve problems. What else we do? What else do we do in mathematics that we do in our everyday life? So far, we have seen two already, very important ones. Problem solving, visualization. Let me show you a simple example. Students learn in fraction. Example, 2/3 share between 2. 2/3 share between 2. มี2ชิ้นแบ่งกัน2คนคนละได้เท่าไหร่ 2/3 share equally between 2. The answer is obvious already, right? When I say it like that. These are thirds. 1/3, 1 piece. 2/3, 2 pieces. 2 pieces share between 2 persons. Every student know the answer because they can think, because they can visualize. I don't need to tell them, boys and girls, you learn how to divide because when you eat pizza, you need to divide. Nobody eating pizza is doing dividing fraction. I can guarantee you that. So a lot of times we do things that doesn't make sense, which is to convince students, oh, you need to learn this, you need to learn this, because when you share pizza, you need to do this. Obviously, no child will believe us. Yeah? But what happened in real world is you think. So, 2/3 share between 2. The answer is obvious. I don't have to do anything anymore. I know this is 1/3. This is another 1/3. And I share between 2 friends. One friend and another friend. So one of them get this, the other one get that. It's as easy as that. Which means each person get 1/3. But you see, we don't teach like that. We don't use visualization for them to learn calculation. The common approach I sometimes see teachers use is, boys and girls, remember the procedure. 2/3 divided by 2. First, you change divide to multiply. And then the second number, you take the reciprocal. And then, you cancel. And then, you multiply the numerator. You multiply the denominator. Why so long process, which don't even mean anything? Just to do something so simple. When they learn using procedure, something so simple, they take such a long process. No wonder students don't think mathematics is applicable. In the real world, when you can think simply, you think simply. You don't go and overthink and make the situation so complicated. That's not happen in real world. In real world, if something is obvious, you don't need to think very much. Like in this case, 2/3 share between 2. A lot of people know each person get 1 piece, and that's it. Why need to make it so complicated? Like this, which don't even mean anything. But you are right. Some of you are saying, but what if it is not share between 2? What if you need to share among 3? Because now 2 share among 3, not so easy. So the students know 2/3 is also 4/6. Same amount. It's like the 2 pieces you have, now you cut into smaller pieces. You get 4. But 4 share by 3, also not so easy, not so convenient. So 4/6 share by 3, also not so useful. So I can ask the students, so can you think Can you think of a good number to change the 2/3 into? What is a good number? Can you imagine the 2 become 4? Not so good. Because 4 divided by 3, not so convenient. So what is a good number to get the 2 to become? And many students will say, well, if I get the 2 to become 6, maybe it's okay. Because 6 shared by 3, that's all right. So I need to know 2/3 is 6/9. So if I know 2/3 is 6/9, then 6 shared by 3, well, that's easy, not so hard. That will just give me 2 9s. I did the calculation by thinking, not by doing a procedure. And this is today's topic, isn't it? How to make students use mathematical processes that they also use in their everyday life. In this example, I am thinking. If I want to be more precise, I am visualizing. I am solving a problem. I have a problem. 2 is not a nice number. It's a problem. 2 is not a nice number. 2 divided by 3. So it's a problem for me. How to change the 2? How to cut the 2 pieces into a nice number to divide by 3. So when I'm thinking, I am solving a problem. In this case, I solve the problem by visualizing. I try to imagine 2 become 4, no good. 2 become 6, that's good. Sometimes I cannot visualize well. What do? I can draw. So when I cannot yet visualize, I know how to help myself. Some students do not know how to help themselves. That is why they are helpless. That is why when they do online learning, the teacher finds so much challenges. When students don't know what to do, they are helpless. They don't know what to do. They give up. That is why we want students to learn how to help themselves. How can they help themselves? Concrete materials. You cannot figure something out, just get the paper, get the stones, get the beans, do whatever you must. You can use drawing. Draw a picture, draw a diagram. You don't know what to do? Talk to a friend, have a conversation, and then maybe we can figure things out. I think many of you do that also in your daily life. Sometimes you got a problem, and then you just talk through it. I mean, some of you do it loudly, but most of us do it quietly. We just talk to ourselves. And for younger children, talking to ourselves is harder, so they talk to a friend. We can figure things out quite often when we talk with friends, right? So, thinking. How to make students see that mathematics is applicable to their real life situation. Make them think. Make them do mathematical processes. Example, problem solving. 2 is a problem. How do I change it to a nicer number? Make them do visualization. Also, can give them diagrams, can give them concrete materials to make them able to visualize better. No? Anything else you want to bring up? You know, just to finish this up, many of us learn the rules. Actually, there's nothing wrong with the rule. It's only something wrong with the way of teaching the rule. If the teacher just tell the students, change divide to multiply, that's wrong. Why? Because it doesn't make any sense. There's no meaning, right? So from Schem's theory, we learn that everything in mathematics must have a meaning. And this is actually quite meaningful. It's not difficult, so it'll be very fast. So you have to pay attention to this one, otherwise you'll finish very quickly. Right? Listen to the language. Something can be anything. Something, if you share between two persons. Okay, repeat telecast. Something, if you share between two, that means each person get half of whatever we are sharing. That's it. No rules. It's just simple logic. Okay, some of you missed it because it's so fast, right? I told you it's not difficult at all. Mathematics is not difficult because mathematics is an extension of what we do every day. So something we say every day. 2 person, each of us get half. 3 person, each of us get 1/3. 4 person, each of us get 1/4. I share this equally between 2. That's the same as to say each person get half of whatever we share. We share this among 5. That's the same as to say each of us get 1/5 of whatever we are sharing. This is using mathematics in daily life and using what we do easily in daily life to do mathematics. Many teachers don't use what students can do to learn maths. All students can understand quite easily. Share between 2, I get half, you get half. Share among 3, I get 1/3, you get 1/3, he get 1/3. It's something they all know. Why teachers don't use that? Today's topic is what they know already in their everyday life. Use it in the classroom. And the thing you are using is called mathematical process. It's nothing complicated. It only becomes complicated when teacher tell them the trick that have no application in real world. Like in real world, when do you change divide to multiply? Like why? You cannot even imagine. You cannot even make sense of it. Because in the real world, we don't do magic things like that. We don't do tricks like this. So this is actually something so easy. You just say it. Probably my Thai is not good enough for me to say it in Thai. Some of you probably can say it more fluently in Thai. But in English, I say it so easily. I have something, share among 4 people. That's the same as to say, each person get 1/4 of whatever we are sharing. If what we share change, then this will also change. If whatever we share is now different, then it's just that amount. In fact, it doesn't matter. We can share whatever we want to share. When we share something among 4 people, we always get 1/4 of whatever we are sharing. No? So, something else you would like to bring up? This morning, I have shared with you 2. I plan to share with you 3 mathematical processes. Anyone else would like to bring something up? Further questions you might have?
Excuse me.
Anything else?
Excuse me, please. I have a question.
Yes, please.
Student told me study math for the university, entrance exam should I change his mindset or not
Right. So can you just ask it in Thai, please? Can you ask the question in Thai language, please?
Huh?
Can you ask the question in Thai?
Okay.
มีครับมีนักเรียนถามผมว่าแบบเราอ่ะเรียนคณิตศาสตร์เพิ่มสอบอย่างเนี้ยจากอย่างเดียวอะครับผมควรเปลี่ยนความคิดของเขาไหมครับ
Okay. So yeah, some students say, "Oh, why I learn mathematics is to pass the entrance to get to university." Nah? So they sometimes have that. Nothing wrong with that. It's a pragmatic or practical way of thinking. Like, why do I study? To get a good job. Why do I study? To get to university. Why do I study? To pass in the exams. I think that's a practical way of thinking, right? And that's their opinion. I don't need to change their opinion. It's their personal belief. There is no need for me as a teacher to try to convince them to change their mind. It's what they are thinking. But what can I do? I can do something to make them realize that learning mathematics is more than just to pass the exams. What I'm saying is, I will not advise them using words. I will not say, "Oh, no, actually, no, not like that. You know, you study mathematics because it's good for your brain. You study mathematics because in future, you can use it. When you become architect, you can use it. When you become engineer, you can use it. Oh, you study mathematics so you can earn more money." Maybe not. But I will not advise them. We all know, not just for this, for everything. When we want students to change their mind, it's not so useful just to tell them. We have to show it. It's the same, even for simple things like behavior. We cannot say, "Don't cheat, don't lie." We cannot just say it like that, right? We have to make them believe it. We call that role modeling. Yeah. So as a teacher, what will I not do? I will not every day tell them in class, "Boys and girls, listen. You don't listen, you will not pass your exams. Boys and girls, this topic is very important. In your test, it will come out." Now, if the teacher say like that all the time, no wonder sometimes they think, "Oh, yeah, maybe mathematics is just for the exams." But you are right, many students are pragmatic. They are practical. They say, "I study because I want to go to university. I study because I want to pass a test." You cannot change that. A lot of people are like that because of their upbringing. Very few people are idealistic. Some of us are, but a lot of people are not. They are practical people, they are pragmatic people, and that's quite normal. But as a teacher, I can try to reduce that. I will not contribute to it. So if I keep on telling them, "Oh, this is important for exams, study it. Like every day, do this 5 problem. Very important for your test next week." If I say that all the time, it will simply reinforce that mindset that you don't want to happen. So don't do that if you want to change their mind. Secondly, just teach them to learn mathematics. No need to tell them, "Oh, you learn mathematics because it's useful every day." No need to tell them. Just do it. Just do it by making them think. If they soon realize that, "Oh, mathematics is just thinking," then they themselves will realize, "Oh, I think every day." So don't have to convince them. Just be consistent in portraying mathematics as a subject where they are thinking all the time. Something else you would like to bring up as we go to the last part of today's session? All right, if not, final example, but just before that, just to emphasize one more time, the idea of mathematics is not procedures, it's not steps, it's not tricks. When students learn to divide 351 divided by 3, 351 share among 3. No? You can ask them, which number is easy to take out? Which number is easy to take out, to divide by 3? I think many students will say 300. Would you agree that 300 is quite convenient to divide by 3? That means we still have 51 left. 51, not easy for me to divide by 3. Any of you have any opinion or advice? If 51 is too hard for me, what number can I take out? Or some of you are thinking 30. Yeah, 30 is quite good for me because 30 divided by 3, that's not hard. And then I still have 21 left. So the 300 is easy. I get 100. The 30 gives me 10. And the 21 gives me 7. So my answer of the dividing is 117. If they learn mathematics like that, meaning thinking, in this case, visualizing, they visualize 351. They visualize 351 as 3 pieces, and 3 very easy to divide by 3, as another 3 pieces. That 3 pieces also easy to divide by 3, and finally 21, which is also easy to divide by 3. So when they first learn it, they use concrete materials. But after a while, they don't need, because ability to visualize. Do you see learning dividing is an act of problem solving? I have a problem. 51, not a nice number for me. It's a problem. How do I solve that problem? I solve it by making it 30 and 21. Do you see, even in learning something basic like calculating, I am doing problem solving. And I'm also visualizing. Today's topic is all about mathematical processes that we do often in everyday life and what it means to teachers in the classroom. So far, we look at 2 major ones that we do all the time, everyday life, but also in mathematics. Solve a problem and visualize, right? And that's the way we want students to have the right mindset. Yeah, I know many of us learn dividing like this. Nothing wrong with this, you know. Nothing wrong at all. I have 351. What number should I take out? I take out 300. It's the same process I just went through a while ago. I just write it differently. I just communicate it or represent it differently. So means I have 51 left. 51 divided by 3, not so easy for me. It's a problem for me. But I can solve that problem by taking out 30, because 30, quite easy for me. And I still have 21 left. The 21, I think I can take out. And as a result, everything is taken out, nothing is left over. And that's good for me because this give me 100. 30, when I divide, I get 10. And 21, when I divide, I get 7. This is a procedure that we learn in school. Nothing wrong with it. What is wrong when the teachers don't teach it using language for thinking? So the language I use is what number can I take out? It's a language of solving a problem. Oh, the number not good for me. 51. Quite difficult for me. The language of problem solving. Not the language of 351. You divide by 3. Actually, I don't even know how to do this because I never taught it like that. But if I say something like procedure, I may say, put 1 here. Why put 1? Oh, just try. 1 times 3 is 3. And students ask, oh, but teacher, I thought we divide. Why you times? And then, never mind, just follow me, okay? When you divide, you times. I also don't know why, but just do it. Step 1, you times. Step 2, you minus. And the student may ask, oh, teacher, I thought we divide. Why we minus? It's just a rule. Step 1, you multiply. Step 2, you subtract. And after that, you draw the arrow. You use a ruler, you draw the arrow. You bring down the 5. You bring it down. So, we don't use language like that. Those language don't make sense. Nobody in the real world talk like that. In the real world, we say, oh, this is hard for me. What can I do? That's the language of the real world. 51 is hard for me. What can I do? It's the same thinking that happened in real world also happen when we do mathematics. Many teachers make mathematics very hard for students because we don't use what they already can do, meaning what they do in the real world, to learn mathematics. Instead, we create some strange things. We create strange things to make them do mathematics. I don't know how to do it properly because I've never done it. And the teacher may say, we need to borrow. Right? And there are some things that I really cannot do because I've never done it as a teacher before. But you know, when the teacher say, you cross this out, you borrow, and I don't know what else, you carry, right? But actually, it's quite simple. It is just 300 It is just 300. I want to take away 100. 25. Take away 100 is not a problem. I got 3 of them. But take away the 20. I don't see any of this yet. So quite inconvenient for me to take away 20. But no problem. I can get 20 out of the 100. Not difficult at all. So the 20 is okay now. But I also need to take away 5. I don't have the ones. No problem. I just get the ones. So all I am doing now is to make the 300 into 200, 90, and 10, which is what we do when we teach students 200, 90, and 10. No stories like borrowing and carrying. It's just solving a problem. I don't have the ones, I make the ones. I don't have the tens, I make the tens. 300 become 200, 9 tens, and 10 ones. And then now I can subtract whatever I want to subtract quite easily. right? So I think that is the main point for today's session. Many teachers are making mathematics overly complicated. Mathematics is actually not complicated. Mathematics is a formalization of what we do every day. That means there's always a link between mathematical processes and everyday life. Final example. Everyday life. From the time the child was a small baby. How does a child know that the animal is a cat? Did the parent explain to the child, hey boy, listen. This is the definition of a cat. No, nobody does that. Right? How do you teach a child that a cat is a cat? One day the child see one cat. And the parent might say, oh, that's a cat. The child may not really understand it, but well, okay, that's information. Then next time, the 1-year-old child see another cat, and the parents say, oh, that's a cat. And the child may be a bit confused, like, oh, it's a different animal. Yesterday was black color, today is white color. Cat, you mean same? I'm sure the child doesn't think like that. But that's the mental processes that's happening. And over time, the child encounter many cats. And although they look different, there are some similar features about those animals. Some are big, cats. Some are small, cats. Some are black, cat. Some are white. Some got many colors. Oh, but they all have something common about them. The human brain is designed to pick out similarities. The mathematical process is called looking for patterns. Sometimes we say generalization. This is the final mathematical process I want to mention this morning. This morning, we have mentioned the mathematical process of solving a problem. Oh, this is hard for me. What can I do? The mathematical process of visualizing. Oh, can I try to see in my mind? Sometimes you say imagining. Yeah? And the final one for this morning, generalization. There are quite many mathematical processes. For the purpose of this morning session, I just want to pick 3 major ones to make the main point, which is looking for patterns is what we do every day. All the time, our brain is looking for pattern. That is how eventually you develop the skill of survival. Because you meet many people, after a while, you begin to generalize that this is a good person and that is a dangerous person. Human brain is designed for our survival. All organisms. That's the fundamental premise. In order to survive as a species, I must do something. So I can survive. So ability to look for pattern is something built into our brain. When our forefathers in the prehistory, ancient times, prehistoric times, see an animal, over time they begin to learn, animal is food, I catch it. See a tiger, that animal is not food, I will become his food, I run away. I see a monkey, that animal might be food, I catch it. I see a lion, I will become food, I run away. So over time, the human species practice these skills all the time, to the point where through the process of evolution, we all have the natural ability to do it. And that brings me to the point about some teachers believe that Some people are good in maths. Some people naturally cannot do maths. That is a myth, meaning not true. It is now conclusive that mathematical ability is predominantly opportunities, is negligibly genetic. There's only a small contribution of genetic to your mathematical ability. In other words, for those of you who are parents, your chance of you passing your mathematical ability to your sons and daughters is negligible. But you can do something about it. By providing the right opportunities, they can either be good or not good in mathematics. Many teachers don't see this. Mathematical ability is opportunity, and the opportunity will make all students good at mathematics if the teachers make use of what students are good at to learn mathematics. Students are good at problem solving because we have been solving problems from day one. When you were a baby, you want the cake, you cannot yet walk properly, you will think of ways. You cannot walk, what do? You crawl towards the cake. The table is too high for you, you cannot reach it. Maybe you take a ruler and try to use the ruler to bring the cake closer to you. We have been solving problems. Likewise, we have been looking at patterns, even as a baby. Looking for patterns, visualizing, solving problems are our strengths. We have been doing it even without much thinking since the day we were born. A baby, when they get hungry, they don't know what to do. They cannot tell the mom, oh, I need milk. So they don't know what to do. They make some noise. And then they realize when they make a noise, the milk comes to them. And then other days, maybe because they were happy, they laugh, they make a different noise. Oh, no milk. And over time, the child learns, when I make a certain noise, the milk will come to me. Even when the baby was not yet able to talk, the brain is already doing all the things that we do in a mathematics classroom. In other words, most of us can do very well in mathematics because we all have the abilities, and this morning we look at 3 of them. Something is hard, what to do? Problem solving. Something I cannot see with my eyes, I imagine it. Visualization. And looking at patterns. Generalization. These are the 3 things we have been practicing since the day we were born. And no wonder we are quite good at them. What is important, classroom application, for teachers is to make use of them. And this morning, I've been trying to demonstrate using several examples what we mean by make use of them. When I teach dividing a fraction, when I teach long division, you see the language I use, right? So, any final questions you would like to bring up? Anyone have something you would like to bring up? I'm just putting on the screen an example of a test item that we give to our students in this school that illustrate the point about generalization, looking for patterns. So the students, oh, by the way, in this school, they do not do multiple choice, because in life, not everything is multiple choice. Sometimes it's multiple choice. You go and buy food, it's multiple choice. You either choose this or that, right? Yeah, some things in our life is multiple choice, but a lot of the harder things in life is not multiple choice. Yeah? So anyway, here, the students are asked to solve this problem in a test. It's a grade 4, Prathom C test. Hans thinks that the sum of 3 consecutive whole numbers is a multiple of a number. explain why Hans is correct. So maybe they will just try to get 3 numbers, maybe 1, 2, 3, and they just add it up, and they realize that that's 6. Well, okay, 6 is a multiple of 2, 6 is a multiple of 3, okay, fine. But maybe I can try 2, 3, and 4, and that gives me 9. Oh, it's not a multiple of 2. I thought it was because I saw 6, but now 9 tells me it's not a multiple of 2. Yeah, but 9 is a multiple of 3. Okay, 6 is a multiple of 3. Oh, maybe the answer is multiple of 3. I can try 3, 4, and 5. Oh, that's really 12. Oh yeah, 12 is a multiple of 3. So I think the answer could be a multiple of 3. In secondary school, they learn algebra, so they may even be able to generalize it. If I have a number m, the number before it is 1 less than m, and the number after it is a number one more than m. If I have 3 consecutive numbers, I add them up, I get, if I simplify this, I get 3m. 3m, where m is a whole number, that's a multiple of 3. So that's how มัธยม 2 students might do it. But younger children who have not yet learned algebra can also do it in a more inductive way. Inductive means you look at many examples and you try to come to some reasonable conclusion. Right? Any final questions you would like to bring up? We are now in a segment where you might have a chance to do a Q&A. Any final questions you want to bring up? Anything from the Facebook Live that
It is a question from the participants in Zoom. Excuse me, sir, can you share her app you use for teach? I mean the application you use in your teaching. I think it is very useful for teachers. Yeah.
The app I use is called Braining Camp. So the various apps I have been using is Braining Camp. Another place you can look at is the website called Math Learning Center. So these are the 2 places where I get whatever app that I need to help students learn. Braining Camp is the one I was using and showing you now. Another one is called Math Learning Center. In the chat, I have also put my Facebook page. I will put the information of the app on the Facebook page as well. Anything else as we wrap things up in the last 10 minutes? If not, can I pass you back to the MC for the closing of the session?
So, Dr. Yap, may I ask
Yes.
you a question? So based on your explanation, so it means that the teacher, I think teaching the student through the process is also important as well, because teaching the process behind the process, we have the concept inside. So we as teacher, we have to understand the concept behind the process, even though we teach the student the process to solve the problem, or how to divide, or how to minus 2 numbers. But the point is that we as a teacher have to understand why we came up with that process, right?
Yes. Very important point you just make.
Yeah, because maybe it will mislead the teacher that we don't teach process of solving the problem, but actually the process is important as well.
Yes.
But the teacher and the student have to understand how do we do the process like that.
Yes. Very important. If the teacher doesn't understand the actual mathematics content, then we cannot bring it across, for sure, right? So for example, division, dividing. The teachers must know that dividing have three meanings. And one of the meaning is in A, how many B? Right? So when we do 6 divided by 2, is in 6, how many 2's? There are 3 2's. So that's the content. And every teacher needs to know that content. We call that PCK, pedagogical content knowledge. Obviously, teachers need to know the content. It's the same for everything. If I don't understand digestive system, I cannot teach biology digestive system. If I don't understand Newton's laws, I cannot teach Newton's laws. If I don't understand economics of theory of demand and supply, I cannot teach that. If I don't understand dividing, I cannot teach dividing. So pedagogical content knowledge is obviously important. So if the teacher know that A divided by B means 3 things, and one of them means in A how many B, then when the teacher teach 1 divided by 1/3, the teacher will say, in 1, how many 1/3? And if the teacher use that kind of language to promote visualization, almost immediately, students are able to see what the answer is. Right? So I think you are right that teachers need to know. Teachers need to know the content. And once we know the content, we can choose suitable everyday language to convey the process. And this is today's topic. What we do in our everyday life, the language we use in our everyday life, how to use that in a classroom to promote some mathematical processes. For the purpose of today's session, we were discussing 3 mathematical processes: problem solving, visualization, and generalization. And I try to illustrate how the 3 is actually used every day when we do whatever we do. And we're actually quite good at them. Important implication for classroom application is the language we use. So I say in 1 how many thirds. I didn't say when you change divide to multiply. I didn't say you find the reciprocal of 1/3. Yes, those may be true, but those are languages that do not promote visualization. When I say in 1, how many 1/3, the brain is persuaded to visualize the task. And once they use something they use every day, visualizing, the answer usually happen quite readily. And that is how mathematics become doable for students. Many students struggle with mathematics because they are not having the right process to get to the conclusion. They use overcomplicated process. To divide, you change to multiply, you invert the reciprocal. It's just confusing and also meaningless. The moment is meaningless, even something easy, we cannot do. The example I always use is, if you ask me to tell you my name, something very easy, right? I think any child can do that. Please tell me your name. If you ask me to tell you my name, maybe I cannot do it. Something so easy, but I cannot do it. If you ask me in Russian, if you ask me in Russian language, please tell me your name. I will not even speak to you. and you will think I'm stupid. Like, how come you cannot tell me your name? This is happening in a mathematics classroom. The teachers think the students cannot do. But it's because the students don't even know what we are asking. The mathematics they learn is a foreign language to them, an alien language to them. It's Russian to them. They don't understand why divide, change, multiply, why you do reciprocal. It's gibberish to them. It's meaningless to them, right? So I think that is an important point for us to remember. Always use language that makes sense. In one, how many, one third. Do not use language that don't make sense. Change, divide to multiply. Like why? Find the reciprocal. But why? Okay. Use language to promote problem solving. Use language to promote visualization. Use language to promote generalization. All right, pass you back to the MCs for the conclusion of the session.
Excuse me.
Yes, please.
Okay. Can I have one more question?
Sure.
Okay. Because from what I listen to you and then try to think about it, everything starts from mathematical problems. So I would like to know that's like where you get the problems from. Is in the textbook or is from the teacher cooperating and trying to find?
It's in the textbook. So Singaporean textbooks, especially the one that I'm responsible for, they always begin with a problem. Yeah. So in my textbook, I call that the anchor task. I will show you one example, but I will show you more example in the Facebook post subsequently. So that is how the textbook that I write look like. So I just pick any grade level. So every lesson begins like that. Janet collects soap containers from different places. You know, some people, they go different traveling and the hotel give them the soap. They like to keep, they collect, you know, soap bottles. And how much water can each container hold? So that was a problem. Yeah. So that's how the book looks like. Or sometimes they have like that. When lines meet, they form right angles. Look for right angles and angles that are larger or smaller than a right angle. So the student always begin with a problem. So your question is, where do the teachers get the problem from? From the textbook. I think some teachers write their own problems, but most teachers will get it from the textbook. Okay? So this is an example of a Singaporean textbook.